Welcome to Operations Research. Today, we are diving into the fascinating world of networking problems. Imagine planning a cross country road trip or laying down expensive fiber optic cables for a city. How do you find the absolute best route or connect everyone while spending the least amount of money? These are the exact puzzles we will learn to solve today. By the end of this lesson, you will understand the hidden mathematical engines that drive our modern, interconnected world. Let us start by understanding what a networking problem actually is. In simple terms, it is a puzzle where you try to find the most efficient way to move through or connect a web of points. Why does this matter? Because in the real world, efficiency translates directly to saving time, money, and valuable resources. Whether you are a commuter trying to avoid traffic or a city planner trying to minimize the cost of laying down infrastructure, you are dealing with a networking problem. We use these mathematical tools to turn overwhelming choices into clear, logical decisions. Before we can solve these puzzles, we need to learn the basic language of networks, which mathematicians call graph terminology. A graph here is not a bar chart. It is simply a picture of dots connected by lines. The dots are called nodes or vertices. Think of them as specific locations like cities on a map. The lines connecting them are called edges or arcs, representing physical links like highways. If an edge allows travel in both directions, like a standard two-way road, the network is undirected. If it is a one-way street, we call it directed. Now that we know the parts of a graph, what do we actually do with them? There are three main concepts we look at. First is the shortest path, which is exactly what it sounds like, finding the route between a start and end point that has the smallest total distance or cost. Second is a spanning tree. This is a special way to connect every single node in the network without creating any closed loops or circles, using the absolute minimum number of links. Finally, we have flow, which represents the amount of stuff moving through the network. To solve these problems mathematically, we must translate our visual map into a language that computers can understand. This brings us to our formal notation. We write the network as the simple formula G equals V, E in parentheses. Conceptually, this allows us to list out all important pieces instead of drawing pictures. In this formula, G stands for the graph, which is the entire network itself. The symbol V represents the set of all vertices, the dots in our system. The symbol E represents the set of all edges, the lines connecting those dots. If the number of edges increases, the network becomes more complex, with more possible routes. Let us dive deeper into our first major application, the shortest route problem. The primary goal here is to find the path of least resistance from a starting point to a destination. How do we do this? We usually solve it using a systematic step-by-step method. We look at our current location, check all the immediate neighbors, and write down the shortest distance to each one. We lock in the shortest one, move there, and repeat the process until we reach the end. Let us look at a concrete example to see exactly how this works in practice. Now that we understand the method, suppose you are at node A, your house, and want to reach node D, the grocery store. We have two possible paths. Let us evaluate the first route, which goes through node B. We are given that the distance from A to B is 5 miles and from B to D is 1 mile. We need to calculate the total distance by adding the lengths of each individual segment together. We substitute our given distances into the equation, adding 5 plus 1. This simple addition gives us a total distance of 6 miles for this first route. This gives us a baseline to compare against our other options. Now let us check the alternative route, going through node C instead. We must evaluate the second option to ensure we are not missing a better opportunity. The distance for this new path is the length from A to C plus the length from C to D. Just like before, we plug in the specific numbers for each part of the journey. We substitute the 2 miles for the first jump and 6 miles for the second jump. Adding these two values together, the total distance for the second route comes out to 8 miles. This will show us if taking the initially shorter path pays off in the long run. Now we have the final numbers for both possible paths. We compare the two options, 6 miles for the first route and 8 miles for the second. We can clearly see that 6 is less than 8. Therefore, the shortest route is A to B to D. Notice something interesting here. The path through C started with a very short 2-mile jump, but ended up being longer overall. This proves that sometimes a longer initial step leads to a shorter overall journey. This step-by-step comparison is exactly how routing software finds the best directions. Here is a visual representation of the exact problem we just solved. On the left, we have our starting point, node A. On the right is our destination, node D. You can see the two intermediate nodes, B at the top and C at the bottom. The numbers on the lines represent the distances we used. Notice the path highlighted in blue going from A to B and then B to D. Even though the bottom path from A to C looked tempting with a short distance of 2, the visual makes it clear how the heavy cost of 6 on the second leg makes it the slower choice overall. Now let us explore our next major concept, the minimal spanning tree problem. Remember, a spanning tree connects every single node in the network without any loops. The minimal part means we want to do this using the absolute shortest total length of edges. A common way to solve this is to simply look at all the available edges, pick the shortest one and add it to our network. Then we pick the next shortest one and so on. The only strict rule is that we must never pick an edge that creates a closed loop because that would be a waste of resources. Let us try an example to see this in action. Imagine 3 villages, X, Y, and Z. You need to lay water pipes to connect all 3. The cost to connect X to Y is $10, Y to Z is $15, and X to Z is $20. We want to connect all 3 for the lowest total cost. We start by picking the absolute cheapest connection available, which is C1, the $10 pipe between X and Y. By making this connection, villages X and Y are linked. Next, we look at the remaining options and pick C2, the $15 pipe between Y and Z. Now, X is connected to Y and Y is connected to Z, meaning all 3 villages are linked. We completely ignore the $20 pipe between X and Z because adding it would create a useless loop and waste money. A spanning tree must never contain any closed circles. To find our final budget, we calculate C total, which is simply the sum of the individual pipe costs we selected. We substitute our chosen values of $10 and $15 into the equation. Adding them together reveals the absolute minimum budget required to finish the water system. The minimal cost to connect all 3 villages is exactly $25. By carefully selecting the cheapest links and strictly avoiding loops, we successfully built a minimal spanning tree. Why do we spend time learning these algorithms? Because networking problems run the modern world behind the scenes. When you type an address into Google Maps, the software is instantly solving a massive shortest route problem to guide you around traffic. When a telecommunications company lays down fiber optic cables for a new neighborhood, they use the minimal spanning tree problem to ensure every house gets internet without wasting miles of expensive wire. Even the internet itself relies on these concepts to route data packets through a web of servers. Without these mathematical tools, our logistics, transportation, and communication systems would be slow, chaotic, and incredibly expensive. Let us review the key takeaways from today's lesson. We learned that networking problems help us navigate and connect complex webs of points. By understanding nodes as locations and edges as connections, we can mathematically find the best ways to move. We explored how the shortest route problem finds the fastest path to a destination and how the minimal spanning tree problem finds the cheapest way to link everything together without loops. You have now covered the fundamental concepts of network optimization. Mastering these basic tools allows us to solve massive logistical puzzles and understand the hidden engines driving our interconnected world.